So today we're happy to have Xuyao, who's working with Matt, and assures me is in his last year as a PhD student here, and he's going to talk about the SYK model and turbulence. And I hope to understand that by the end of the hour.
Okay, so my Brown Bag will be based on my recent work done with Vladimir Rosenhaus. This is an archive number. Vladimir is a faculty member at CUNY Graduate Center. So in this work, we're trying to propose a classical theory, which we think it should be think of as classical version of SYK model. As you will see, and this theory is inspired from the turbulence study. So for today's talk, I'm going to it contains 3 parts. So in the first part, I'm going to first introduce you to SYK model, which is a quantum model of n fermions. And I will tell you what is SYK model and why people are interested in this model. And then in the second part, I'm going to tell you the story underlying the model we think should be as the classical version of SYK model. And the story is about turbulence. So in the second part, I'm going to do a brief introduction of turbulence and tell you how this model arises from the turbulence theory. And the theory I'm talking about here is the so-called random coupling model, which is a classical model. And in the last part, I'm going to show you why we can think of that as a classical version of SYK model.
Just to orient myself, we're talking about like turbulence of fluids.
Yes.
Okay.
And the plasma.
And plasma.
So let me start by introducing the SYK model. So the SYK model is a quantum model. It's a quantum system made up of n fermions. With random couplings, and these couplings are all-to-all couplings. So to define a quantum theory, let me just first write down the Hamiltonian. So the Hamiltonian let's write down in this way. So we have n fermions. So the coupling carry 4 indices, and we have it's a quartic. Let me talk about the original SYK model. So the interaction is described by the quartic. So we have a quartic interaction. So the size are fermions, which means they satisfy the Clifford algebra. And what's special about this model is that these couplings, they're just random numbers drawn from Gaussian distribution. So these couplings are random. So to describe a random number, we just set, let's say, the mean value of this random variable is 0, and the variance is given by some number. So here n is again the total number of the fermions we're talking about, and j is a constant. And because we're dealing with fermions, and you know fermions are anti-symmetric, that means so for this coupling, these couplings has also to be anti-symmetric, which means if you exchange 2 indices, that will give you a minus sign. And also, if you put 2 indices to be the same, then that will give you a 0 by just anti-symmetry. So that is, for example, IJJL is 0.
Excuse me.
Yes.
Sorry, just a silly question. Can you explain why the coupling constants go down? Is there more Barbian?
In this.
Yeah.
Because-
Why is J proportional to? I don't need to know why it's proportional to 1 over n cubed. I just need to know. I'm just curious why it's inversely proportional to the number of fermions.
You mean this order or? This
No, like the coupling. Sorry, the variance. Is it just yeah?
Yeah. So so you're saying well, this is just a normalization. You can take this thing to be like a constant here, but it has to be well, the variance we put it by hand that it scales in this way. Otherwise, so the goal of having this random coupling is to have some analytic control over this model. So as you will see, this thing plays a critical
Isn't
role.
that just a definition of J squared?
Yeah.
Where does J depend on the number of fermions?
No.
It's like
So it wouldn't be a definition, right?
J is some constant you can set.
you can say the definition in terms of the JIJKL, definition of capital J. Presumably, you're going to take some limit as n goes somewhere, and then you
Yeah.
want J to be
You want
constant.
J to be fixed.
Yeah, J's fixed. Yeah, and we wanted to go to 0 as you. You want them to not be coupled as
want it to
the
be
number of
weakly
fermions goes to infinity.
It's roughly speaking because they're all coupled to each other. So as you increase the number towards infinity, you have more and more, you have stronger and stronger coupling unless you decrease the strength of the coupling in some inverse power event. That's 1 over n cubed is not obvious from that, but there should be some inverse power.
Okay.
Okay. Well. Okay. I will show. Well, this n cube inverse will actually be very useful for this model, and I will show that in a moment. So to understand the dynamics of this model, I drew this picture. So basically, you can think of those fermions sitting on different sites. Although this is just one way to think about this model. So on all these sites, you can just rewrite the size. You can write down the creation annihilation operator in terms of those size. So this C dagger and C are just linear combination of those size. So equivalently, you can write it in this way. So we can talk about this picture. So the fermions are sitting on these sides, and the shaded dot means on that side the fermion is excited, and the empty side are just the vacuum. So the annihilation operator kills. Will turn a fermion excitation to a vacuum. So let's think about just one term in this series. You can think of the interaction as a as a transition or collision of these fermions with some quantum transition amplitude. For example, if you talk about this single term, that is a coupling between coupling among 1 at the first site, 1st, 8th, 11th, and 19th site, and this will just give you the dynamics of this transition with some transition amplitude. And you have a large summation of these things, so there are a lot of things going on simultaneously. So this is one way to think about the SYK model, the dynamics of the SYK model. Now we can ask a question. So clearly this model is just made up. So it cannot, it's not a realistic model.
Are you talking about zero-dimensional model or one-dimensional? Are the fermions time-dependent, or are you talking about zero-dimensional model?
I'm actually talking about 0 plus 1.
Zero.
So this size depends only on time.
And there's no space at all. It's just that you have some n states that are just changing their occupation numbers. And they can only be 0 or 1 because they're fermions.
Yeah.
And then one other just stupid question up at the top of the Hamiltonian, you ordered IJKL, that's just to get rid of all of this redundancy here, right?
That's right. That's
You ordered them so that you don't have to deal with the parity and the
That's
zeros.
right. That's right. Because only those things are independent.
Right, fine. Fine, so if I did the naive sum, I'd have to divide the j's by some big combinatoric factor.
Yeah, 1/4 factorial.
Yeah, right.
That's the big guy. Okay, so SYK model. Just use this one. It's not a realistic model because if you think of this model in this way, it doesn't have a notion of locality. And this is ridiculous in the sense that you have, well, let's say the model tells you that you have to go through all the choices of 4 sites. So you pick any 4 fermions in all within these 10 fermions, and just assign a random number to those 4 sites and call that is the coupling. So suppose you are thinking of the model in this way, you can pick 1 fermion here and 1 fermion there. They're very far away, but they are still interact with each other. So there's no locality. And in a real system, like a real life system, we barely see these things. And the second thing,
But you have no space, so if
that's right.
if these were like, instead of being 21 fermions in a 0-dimensional space, these were like 21 fermion fields through all of space.
Yes,
There'd be no locality issue, right? Because
That's right. that's right.
because they would all be co-spatial everywhere.
That's right. That's right.
Yeah.
So this issue is just
It's just
it shows up when you think.
conceptually it's
That's
there, but it's not
Yeah.
really.
Yes. So the second issue is the random coupling. So this random coupling is just you set it by hand. There's no physics about this ensemble. So it seems that this model is useless. But actually, people are doing more crazier thing than this.
That's a
And more
that's a
crazy
dangerous
story,
criterion.
and more crazy story will work. And the story is the thing of random matrix theory. So when people look at the nuclear physics, they try to look at the spacing. So they look at the Hamiltonian spectrum, and they look at the nearest spacing between those levels, and they do the statistics. So this system is very complicated. People cannot write down a Hamiltonian describe such a complicated system. So what people do is just they say, okay, our Hamiltonian is some matrix, and for each element, they choose a random number, subject to some symmetry. So they find that this thing will reproduce very, very nicely. So this, the spectrum of this, the statistics of this spectrum is very consistent. Is consistent with the nuclear physics data.
Some regime, presumably, could you tell us? I mean, like very massive nuclei or something. It's probably not true for helium.
Yeah, it's like heavy nucleus. Yeah, but yeah, the specific regime I just don't remember. Yeah. So people do this. So SYK is actually less crazy than this because we still restrict ourselves to just like full body interaction. We're not doing like that purely random thing, a completely random thing. So this leads to our second part. So this model seems useless, but why are people interested in this?
Anyway, just as a comment, there are a number of people that do quantum experiments where they have trapped atoms or ions,
Yes.
and then they try to introduce all-to-all interactions between them, even though they're separated spatially with
Yeah.
two electric pulses of various sorts.
Right.
So I don't know if anyone's trying to realize this would probably be pretty hard with the one particle interaction, but but at least for non-local 2-to-2 interactions, features like that.
Okay.
With two-part interactions. So it's possible to make things that are non-local.
Yeah.
Speaking of the law.
Thanks for the comments. So, so why are people interested in this model? The first thing is that SYK model is solvable. At large n, which means you take n to be infinity. This thing is solvable for very large n. The higher order terms will be suppressed. So this point is a very critical feature of SYK model, and I'm going to elaborate this in a minute because it's relevant for my thing. So the second thing is that SYK model is maximally chaotic. So, so you may ask, what do you mean by chaotic in a quantum system? So let's remind ourselves that in a classical system, let's say we consider two trajectories in the phase space. If you start from two very near locations and evolve with some time, you will see if the system they separate so close in the phase space initially, and then the separate between the two location in the phase space becomes extremely large. This is called if this is true, we call it it's a chaotic system or classical system, and this exponent is the Lyapunov exponent. So people get the quantum variant of this quantity in like the quantum model. I'm not going to tell you the details about that, but there's a quantity called out of time order correlator. If this thing grows exponentially with time, then they call this Lyapunov exponent. And people, in general, computing this OTOC thing in a theory is not easy, but this calculation can be done in SYK because it's solvable. So people find that for SYK, the lambda, the Lyapunov exponent, if you consider this OTOC in the thermal states, yes.
So in classical chaos, the Lyapunov exponent depends on a particular trajectory, a particular point in phase space.
Yes.
For the OTOCs, what's the analog of that?
It's like, OTOC is basically the exponent of two operators, one at 0 time, the other as a t time, and you take the commutator.
Yeah, I know it's clear. I'm asking what's the analog of the state dependence in classical chaos? I understand the demolition.
State dependence here.
In classical chaos, the Lyapunov exponent depends on a particular trajectory, a particular point in phase space.
Yes,
It's not the same for every point in phase space.
that's right.
What's the analog of that for the OTOC is what I'm asking. I know what the definition is.
I would say for different states, you will have different prefactor here.
Yeah. No, sorry. For classical chaos, lambda is dependent on a point in phase space. Not the prefactor.
Okay.
The exponent.
Oh.
What's the analog of that for OTOCs?
Well, so in classical system, you can talk about the maximal lambda.
Good.
So that will remove the state dependence. I'm thinking of this thing. You should think of that corresponds to the maximal lambda in that model. So for SYK, if you compare the OTOC in a finite temperature state, that is the beta is 1 over the temperature. The exponent is given by this. And people have conjectured and proved to some extent for a quantum system, if it is chaotic, the Lyapunov exponent should be bound by this number, which means SYK. But in this sense, I'm saying that SYK is a maximally chaotic system.
Question?
Yes.
Is there a reason why lambda does not depend on G? Or like should it depend on G? Just trying to get some.
Good question. So it depends on J. I should say that this is at strong coupling. So if you plot the lambda, it should this. So at strong coupling, it saturates this number. Thanks for that.
This is a large n, right? When n goes to
Yeah, larger. So so there are other two aspects about SYK I'm not going to elaborate on. So we'll find that the low energy sector of SYK has a dynamics that you can also find in 2D dilaton gravity. So which means it's possible to have some dynamics that can be used to describe gravity by this dummy model. And the last part is that people can use this model to study like phase transitions in condensed matter theory, because for this model firstly it's solvable, so you have all the analytic control, and then you can use that to study the details of phase transitions. So this is why people like doing this. But now I'm going to tell you another story, which is not a quantum, but the goal is to find. So last year we asked ourselves a question: whether there is a classical system that has dynamics similar to SYK. So we look up those literatures, and we found in old literature of turbulence, there is a model.
Wouldn't you say the gravity is already such a example?
I'm sorry?
Wouldn't you say gravity is already one such example?
Okay, yes. Then
We're looking for another one.
Yeah, another one. Okay.
And just one quick question about the previous blackboard. So can you remind me, so the span on chaos lambda, that's valid for any quantum system? Doesn't depend on space time dimension. It's the same formula? Or you also depend on space time dimension?
I don't remember the details. Sorry.
And is there an assumption on the operators V and W you should choose?
I think so. I think so. Yeah.
But maybe to be generic, light, heavy. What is the?
Well, I'm not sure.
Okay, but it's irrelevant for your.
That's right.
One thing you can say about it is that if you analytically continue T,
Yeah.
then this is the statement that this OTOC is periodic with period by beta, which is a formal
Yeah,
statement. So
I see. So the derivation holds each other.
I don't know to what extent it's a derivation.
But it sounds
yeah,
intuitive.
Right, that somehow thermal systems become chaotic as rapidly as anything.
That's a statement about the state, right? Not about the operators V and W.
Yeah, I don't think it's supposed to depend on the operators, but there is some assumption about operators.
Yeah, I just wonder if there's kind of the same level of dependence as in ETH or something.
Yeah, it's something like that. And if you make the operators very, very high dimension, then you can mess it up.
Yeah.
Destroy the state with the operators.
Okay, let me move on to the second part, which is turbulence. And the model I'm going to talk about, it's called random coupling model. So basically the random coupling model is a classical model describing the dynamics of Fourier modes of velocity fields in the fluid, especially in the turbulence. So to give you an intuition about why we want to get this model, let me do an introduction of turbulence. So if we start talking about the turbulence of water, so we start by writing down the dynamics of the water, which is governed by Navier-Stokes. So this is the Navier-Stokes equation. Let me first write on it and explain the quantities. So here U are the velocity fields of the fluid. This nu is the kinetic viscosity. Rho is the density of the fluid. P is the pressure. So if we consider incompressible fluid, that means the divergence of the velocity is 0. Then by taking the divergence of the whole equation, we can just express the pressure in terms of U. Then you inserting that expression back into this, you will get just a nonlinear equation, which involves only U, and also the nu's. So the next step, we are going to consider the fluid in the box. So by putting the fluid in the box, you can express the velocity field in terms of Fourier series, and those modes are discrete. So that means we can just write it down. And here we have y, x. Okay. So these are the modes we're going to focus on. So in terms of these modes, we can rewrite this thing in a discrete form. So let me just write that thing down. And now I'm going to suppress the t dependence here, but these variables actually depend on time. So this is a constraint sum. So let me explain. This is a projection operator. You can do this exercise by inserting this to this equation and get the discrete form of Navier-Stokes. Now notice that both the spatial component indices I and also this k, both of them are discrete. You can rearrange this quantity in a sequence denoted by phi with a sub alpha. So there is a map between the alpha and I and k. I'm not going to write down an explicit map between these variables, and this is done by Kreishnan, who was a leader of the turbulence study, and who was also a previous faculty member at the Kura Institute at NYU. So this is
I and X is what? I and X is like components, X,
Yeah,
Y,
yeah,
and Z?
yeah, like
I is X, Y, and Z, and K
That's right.
is the K vector.
That's
Fine.
right.
And K is I is an index, K is a discrete set of 3 vectors.
yes,
Got
that's
it.
right.
And that goes to states alpha.
yes, and you can have a sequence of that, and alpha is just some linear
Got
number.
it. Good.
So you can look at this paper. This paper tells you how to rearrange things in this way. So now we're arriving at an equation for phi. So let me call this alpha. So it has this abstract form, which is the following. So as you can see,
I think I'm losing it a bit, because there's so many things. There's the PIJ,
that's right.
which is something I guess you have to solve for, and the Ks are the indices. So could you, like, should I think of phi as sort of wave functions for the turbulence, or what should?
Well, the phi's are just these u's, and I pack all this stuff into a variable a.
But in that equation on the bottom, you have a summation that you write down explicitly. That summation is over k prime and k double prime,
Yes.
right?
Yes.
Whereas, but you also must have a summation over m and
That's
j.
right. That's right.
Okay.
Yeah, that's right. So now we have this equation. What can we do with this? So then the next step. So far I didn't tell you anything about turbulence, but just write down this equation. So now I'm going to tell you the story about turbulence, and the goal is to just remove the viscosity term.
So I mean, I'm asking stupid questions here, but the PIJ
Yes.
here
Yes.
is something you can just directly derive from the equations plus the boundary conditions, right?
Yes.
Literally, it's just somehow solving all those ridiculous equations.
Yeah, it's given by this.
So there's nothing random here. You're about to say that you can treat A, alpha, beta, gamma as a random matrix, right?
There's nothing random in there, but when time evolves, especially when you get the turbulent regime, this thing can be hard to track.
I see, yes, I see. So effectively, the state itself becomes somehow like a random.
Yep.
Yeah, okay, good. I think I'm nearly there.
So
The Ki, Kj are constant over time. Why do they depend on time? Delta Ij is just I don't see how this becomes changes over time.
well, time dependence.
Yeah, UI are different. Yeah.
Yes.
He's putting all that together into these alpha, beta, gammas.
Phi.
They're in
Phi.
phi, right?
They're in phi. Yeah.
Fine. So okay. Is there any other questions?
You haven't answered.
Oh, okay.
Why?
Sorry, what is that question?
I can't believe.
But the question is, how do we think about phi? Is it like
Phi is UJK. It's just that you take the two indices, the J and the K, that are just discrete indices, you call them alpha. And instead of calling this the field that depends on them, you call them phi. So phi 1K is U1.
so is it
Phi
kind of
2.
like a
No, it's
helicity
U.
torsion?
It's U. Phi is
Phi
U.
is you.
It's
Phi-
just
phi
U.
is
Product
just
of views.
you.
Product of views.
No, it's not a product of U. It's U.
It's
Phi
just you.
is U.
It's a Fourier model.
It's so simple, right? Then you just change you just take U1, you call it phi 1. U2, you call it phi 1 alpha.
Perfect.
You just relabel the indices.
Yeah.
Now, we don't see how it is.
Yeah, we still haven't answered the question of where the randomness comes in, but probably you will.
Well, he hasn't even said it.
Yeah.
It's random.
Yeah. So go.
Well,
Keep going.
This is a nonlinear equation. You can actually track it. You can take some initial condition and just evolve using this equation. But I mean, it's a nonlinear equation, so it has initial condition sensitivity, which means it will have the Lyapunov exponential growth thing. And in order to talk about some observable and make sense some observable, you have to you don't want to talk about some erratic changing thing, but you have to talk about this quantity averaging over something. So
I would keep going, and you'll probably answer the questions in our.
okay, so let me talk about the turbulence. So in the water, if you pass the water through a cylinder, you will see the turbulence happens defined. It's right here. So what will happen is that you first will see some large eddies.
Is there a condition on the velocity of the, there's a condition on the velocity of the water, right?
Sorry?
The velocity has to be larger than, like, if I take this water
That's
and
right,
move
that's
very
right.
slowly, it will not be.
That's right, that's right. That's called Reynolds number. So the turbulence will happen when Reynolds number is large. And the Reynolds number is defined in this way. The U is the magnitude of a velocity. The L is the size well, as you say, I will tell you what L is, and the nu is the viscosity. So when turbulence happens, you will first see some large eddies formed. Those large eddies are created by the inertial instability. So you will have those large eddies in the water. So the size of the largest eddies is basically capital L. So when turbulence happens, this Reynolds number has to be very large. Otherwise, you will just have a laminar flow. So when turbulence happens, these large eddies were formed by inertial instability, and they will break up to smaller eddies still by inertial instability, and they break up to even smaller eddies. So in this process, the energy passes from the large eddies to smaller eddies. And when the eddies are very small here, let's say the size is just eta, and the size is so small that the Reynolds number based on this thing is of order 1. That means at this stage, viscosity comes into play. Which means in this range, we call inertial range, you can just ignore viscosity. So the process is like this. Energy passes from large eddies to smaller eddies, and at some later time, the kinetic energy of the fluid is dissipated by the viscosity. So if we talk about the fully developed turbulence, and we focus on the inertial range, and at any instant here, there are like large eddies, and there are also smaller eddies occupy the same position, and they will interact. So if you talk about this scenario, we can just get rid of the viscosity for this range. So that will give us the phi alpha dot is given by this. So what we did is that just ignore the viscosity term. So the question now is that we want to solve this equation, but it's nonlinear. It's very hard to solve it analytically. And the nice thing about turning off the viscosity is that there is a conserved quantity. So initially you can say this thing is just the Fourier mode squared. And in terms of phi, you can just do a simple check. This quantity, well, it's conserved if you turn off the viscosity. So if this quantity is conserved, this will impose a constraint on this the coupling constant. So and also you can remove the zero modes from this equation, because if k is 0, then you will see so those ui of k equals 0 are just conserved with time. If you do that, that corresponds to you set like A alpha beta beta or A alpha alpha beta is 0. So we have another constraint for this coupling constant. And so now I haven't said anything about random coupling. So as I said, in turbulent regime, in the fully developed turbulent regime, what we want to do is to get a statistical theory, not a theory that gives you different times. Well, that gives you quantity very different for each time. So for example, let me just draw it right here. If we want to measure the velocity field at some later time, for example here, let's call this the x.
Is there like an intuition of why you get like antisymmetric A when you don't start with fermions? Because they are, well, by the construction, the fermion is occupied 0 or 1 or nothing else. But they are like that sort of Yankee identity and antisymmetry and the coupling. Is there any reason
what fermion to do with this? This is phi is the velocity.
So phi here is bosonic.
Yes.
If you don't impose any constraints on the coupling constant, you cannot do this. So this is just a physics context which can give you constraints on those, because as you know, these are bosonic field. So you don't have the anti-symmetric thing on this, but you have to impose something else.
Comes from conservation.
Conservation of energy is antisymmetry in couplings. Conservation of energy gives you antisymmetry in couplings.
Yeah. So
doesn't tell you it's anti-symmetric, it tells you the totally symmetric part vanishes.
It's symmetric in beta gamma, right? On the nose.
It tells you the totally symmetric part vanishes, but there's mixed symmetry structure.
So okay. So let's say we measured the velocity field at this point for the turbulent regime at some later time. If you just start, so this is, let's say this is a one realization. If you start with some initial conditions that's very close to this, but you still will see something very different at a later time. So this means that let's talk about what we want to measure in the turbulence. So what we want to measure in the turbulence is some quantity, average over something. We want to have a statistical theory for the turbulence. So the something could either be initial conditions, external forcing, or space, or time. So so that's the thing we're going to do. So let me tell you what is the random coupling model. So the random coupling model I'm going to write down is not in the context of Navier-Stokes turbulence, but it's in the plasma turbulence. But the spirit are the same, but the only difference here is that I want to make contact with the SYK model. So now I will have a cubic term on right hand side. So this particular form is studied is studied in the plasma turbulence context. So it's studied by Hansen and Nicholson. This paper. So now we make this J coupling as a random coupling. Make it random.
Question,
Yes.
what is the index I? To J?
Oh, I'm sorry. Here I have
Oh,
I.
here, okay.
Sorry. Thank you.
Thank you.
So now we make this random coupling, but this random coupling has to satisfy some constraints.
Sorry, but so there is no relation to turbulence right now, because in turbulence A is fixed, right? I mean, A can be computed in terms of E and K. There is no,
Yes.
no randomness there. So what's the relation?
I mean, well, in this regime, as I said, there are a lot of modes that are interacting with each other. And suppose you keep flowing the fluid here, and there's an energy cascade. After this energy cascade, I don't think you can.
The A are just K times Pij, and Pij is the projector over transverse modes. So the A are completely fixed. You must, I mean, to get something random, you should not compute the phi at each K, but maybe take an average over a range of K, or take an average over time and write another equation, which is not this one, but is an equation for the averages. And
I mean, for average of phi.
Of phi, yeah, over either an interval of time or an interval of frequencies or a space region, right? Because otherwise, if you work microscopically, I mean mode by mode, if the phi's are in one-to-one correspondence with the U, A has nothing random. A is there.
That's right. But if you do so, you say we just change the interpretation of these phi's, but I still can have something like this.
And probably also higher order terms expect when it will be average.
Right. But I think the point is very good. So we do cutoff of the case, because so here we are ignoring those terms. So we do cut off the case, and I think we also need to focus on some subregion. And yeah, I think that's the thing.
So I mean, if you do that, if you do an average, then there will be a lot of terms, because A will be just the first, and then you have many, many more. You may argue that you start always quadratic because it's the lowest nonlinear interaction that you can have.
Right.
On the other hand, there you start at cubic order. So why is it? I mean, what's special in this model that doesn't start quadratic? I expected if you write a random nonlinear equation, it would start quadratic.
So in this model, these phi's are like the Fourier modes of the electric field in the plasma. So people do get another, which is not Navier-Stokes, but another equation that governs the dynamics of the electric field in the plasma.
But does it start cubic because of some symmetry argument? Or
yes, I think so.
Charge conservation signature. The phi charge conservation on.
So, okay.
So we've abandoned turbulence now.
Sorry?
The application is no longer water.
It's no longer water. Yeah.
It's still turbulence, just in a plasma.
Yeah.
Okay.
But I guess there's no analogous Z2 selection rule in Navier-Stokes.
But no, because you can write the equations.
Right, but I mean, if SYK is supposed to be the have Navier-Stokes as the
Participate
limit,
conservation.
then where does that
In Z2,
or I mean, you want it, you're somewhere in your points that you were saying that SYK you think has Navier-Stokes as some kind of limit. But Navier-Stokes doesn't have this discrete symmetry, so.
well, here I'm saying I discretize Navier-Stokes. I'm not saying it's SYK.
Okay, but I thought you said that on one of your.
Well, what I'm going to do is to tell you this model is inspired from the idea of turbulence, and I'm going to show you this classical model. It has some similar dynamics to SYKs. That's what I'm going to do. Okay. 10 minutes. So there are constraints on this J's. Because we're dealing with bosonic field, we know that these last three indices has to be symmetric, and any exchange of two indices in these last three indices. So let me write in this way. I'm going to distinguish the first index. So IJKL is now equal to IKJL, for example. And the second thing is that we have the cyclic sum vanishing condition. That is KLI plus JK plus JLIJK is 0. And also we impose constraints that if you have two same indices is 0.
So two follows from conservation of some energy.
Yes, I think so. So as I said, we want to have a statistical theory of turbulence. That means our observable has to be something average over something.
So you have symmetry here or anti-symmetry?
Symmetry.
These are like electric field.
Then why is IJJL 0? That's just setting it, or?
Well, it would be automatically it was antisymmetric. Here you have to impose it as an extra condition.
Yes. It's a natural condition that you impose. So let me talk about the quantity in the turbulence. So this is observable. It's a quantity. It's an expectation value of some quantity, which that quantity is a function of those phi's at different times. And we're going to average that over realizations. So for each realization, you may have different initial conditions. So that means we're going to draw. So this is what I mean by the observable. Let's say, for example, you can talk about the 2-point function, then you can take, well, maybe you cannot see that. We can take the O quantity depends on 2 times. There are phi's at different times, and we pick the initial value distribution as a Gaussian. So let's say it's Gaussian. And the reason that we introduced the random coupling is just because, just as SYK, we can have analytic control over this model, which means we want to make use of that.
Yes. What should it be Gaussian if the theory is highly interacting?
And that's the initial condition.
Initial condition.
You choose them. You choose them.
Yeah.
Random around some point.
Right. So we want to take the second average over the couplings. So now you will have some distribution for this random coupling. Well, now this distribution is different from the SYK case, because in SYK case, you choose your coupling from a free Gaussian distribution. But now the distribution you take has to satisfy these constraints. But but now I'm not going to write down the detail about how we construct. If you are interested, you can look up our paper. But the thing I'm going to tell you is from this theory, we can solve the 2-point function. So we can get the equation of motion for the 2-point function. And the way we got that, you can also draw if you know SYK, you know that if you do the perturbation theory, and in the larger limit, the 2-point function will be dominated by the so-called melon diagrams. So in so here we also have those things which, well, let me just draw a few of them. So this looks like a melon. So in the larger limit, you will see that the 2-point function is dominated by these kind of diagrams or this kind of diagrams. Of course, you will have to do the average over the j's. These are the only diagrams that will be left will be left in this series. All those diagrams will be subdominant. That means they will get an extra 1/n to some power factor, and when you take a large n, you can see this goes to just 0. That's why we say it's dominated by this melon diagram, because for these diagrams you don't have this suppressed prefactor. So in the turbulence theory here, because we have these constraints, so we developed melon diagrams. We will also do the perturbation theory for this theory, and we find that the 2-point function is also dominated by the melon diagrams, but it has some new structures. Grammatically, I will draw it in this way. So this arrow just reflects the fact that we distinguish the first leg. And those little box there, they are just I squared. You do contraction and you do this average. So we also have those melon diagrams for this theory. The more systematically, if you want to solve for the 2-point function, you have to do path integral. So we do a path integral for this classical theory. So in the classical theory, all we have is the equation of motion. So the way we do it is to attach, well, you attach another integral here and enforce everything satisfy the equation of motion. So you can rewrite this delta function by introducing an auxiliary field. That is the rho field. You can just write it in this way. It's rho times the equation of motion. Equation of motion is just this. You put everything to left-hand side, that's the equation of motion term here. So we solve this. How to solve this? We introduce some bilocal fields. One of the bilocal fields is the 2-point function we're going to focus on. And then we are going to do this integral because actually this part is quadratic in J, in the exponent. And here, equation of motion gives you a linear term in J. So this integral is just a Gaussian integral. So you can do that integral. And we are going to integrate out rho, this auxiliary field, and phi. And finally, we will get, we introduce 3 bilocal fields. Because in SYK, we introduce the phi, which is the G, which is phi summation. But now, because we introduced the rho, so now we will also introduce like a rho thing and the rho phi thing. So we have 2 actual bilocal things here. And also we need to introduce the Lagrangian multiplier for that. And after at the end of the day, you will get this form. So we will have a quite complicated effective action with some large parameter here. So we can say that this thing at large n is dominated by the saddle point. Right, the saddle point, so we can solve the saddle point equation, which means we get this effective action, and then we vary the effective action with respect to the bilocal field we introduce. And we will get a bunch of equations, and we solve those equations. And by some ansatz, we get the equation. And let me just write down the final results, and we will wrap up. So the final result is an equation for a 2-point function. So it's just the 2-point function time derivative is given by minus 3j squared over t, and the j. So the j squared comes from this thing, and also so j dot is related to j by some normalization. So the final result is the following. We have g of t minus s. So this is the random coupling model. And for SYK model, if you look at the Euclidean 2-point function, the Euclidean time ordered or the Feynman 2-point function, this thing is given by this. Tau 1, let's say that's tau minus tau 1, and g of tau 1. So you can see they took very similar form. And so in this sense, we can say that we can think of random coupling model is a classical version of SYK model. And yes.
Can I ask you a question?
So why don't we say thank you
Oh, yeah.
to Xuyao, and then we can have
Just I mean, a curiosity. So the SYK model is, at least I mean, as far as I know, is known to be replica symmetric, right? So in your random coupling model, when you do the average, I mean, and I guess also you have like a replica analog of this calculation. Is the replica symmetry broken here or not? Like, if you do the replica symmetry calculation, you get these results? Like the replica symmetric ansatz. So basically, the simplest one.
Well, I don't know.
Or actually, let me rephrase it. Like, when you compute the center point equations,
yes,
then of course you have to compute the Hessian to see if your solution is stable, right? Otherwise, I mean, you can be a minimum in a center. So when you compute this, I mean, if you can compute this Hessian, do you see any negative eigenvalue? Like that tells you that this, I mean, that there is like any.
Well, that's a good question. I haven't looked at that yet.
So I don't know if this cubic classical model with these imposed symmetries and random couplings is meaningful, but if it is, then you can easily check your results by running a numerical simulation, because those are just real numbers. Did you do it, and does it confirm your funny integral equation?
Yes.
It does.
Yeah.
So in this sense, perhaps it is some meaningful analog of this SYK or something, right?
Yeah.
That's interesting, right? So I mean, by itself, this system probably does not describe nothing, but if it is indeed reproducing more almost, is it exactly the same equation?
So
this
the difference
thing
is the overall sign here and some normalization factor, and also in SYK you have gamma term here.
But so then can you say it somehow helps you understand this SYK or whatever, right? Because as a classical system, surely, who cares? But
well, in SYK model, actually the G here is the time order thing, which is actually different from this thing. Well, this thing is basically a 2-point function. You calculate it in some particular state. But SYK model, what they're calculating is like the Euro QFT. You calculate this thing between the in state and out state.
so it's not like a mathematical isomorphism which helps you solve SYK or whatever, right? It's just this kind of loose analogy or something.
Right.
I see.
think he wants to calculate turbulence.
No, turbulence, forget
No.
about.
There's some words I
This
can
has
say
nothing
about
to do with
this.
turbulence, that's all.
So if you do like Schwinger-Keldysh analysis of SYK, this thing should be thought of as the classical analog of the Keldysh two-point function. And but in the process of getting this, we actually insert an n-set for this bilocal field. And you can think of that bilocal field as the retarded Green's function. And they are related by something like the fluctuation dissipation theorem. So I would say if you want to start from SYK to get something exactly like this, you can do Schwinger-Keldysh and take the classical limit. You won't get the exactly the same form, but you will get some similar form as this. I mean, that will just get rid of this.
So we're a little over, so let's thank Xuyao again, but people who
Are you running this for you? So we've been working on this.
Well, they-